Alright, so in this video, I'm going to be explaining this important paper with the title Equiformer, Equivariant Graph Attention Transformer for 3D Atomistic Graphs. This I clear paper in 2023 from MIT. Despite their widespread success in various domains, transformer networks have yet to perform well across datasets in the domain of 3D atomistic graphs such as molecules, even when 3D-related inductive biases like translational invariance and rotational equivariance are considered. In this paper, we demonstrate that transformer can generalize well to 3D atomistic graphs and present equiformer, a graph neural network leveraging the strengths of transformer architectures and incorporating SE3 quotient E3 equivariant features based on irreducible representations. First, we propose a simple and effective architecture by only replacing original operations in transformers with their equivariant counterparts and including tensor products. Using equivariant operations enables encoding equivariant information in channels of irreducible representation features without complicating graph structures. So atomistic systems are often described using coordinate systems. For 3D Euclidean space, we can freely choose a coordinate system and change between them via symmetries of 3D space, 3D translation, rotation, and inversion. The groups of 3D translation, rotation, and inversion form Euclidean group, with the first two forming SE3, these translation and rotation, and second being SO3, and the last two forming O3. So the laws of physics are invariant to the choice of coordinate systems, and therefore properties of atomistic systems are equivariant. For example, when we rotate our coordinate system, quantities like energy remain the same, while others like force rotate accordingly. So transformation matrices of group elements like G that act on a vector space X, we call it group representation. For example, for 3D Euclidean group, we know this is E3. Euclidean vectors can be projected into type L vectors by using spherical harmonics. Tensor products can interact different type L vectors, and we discussed tensor products for SO3 and those of O of 3. So we propose a simple architecture equiformer with dot product attention and linear message passing by only replacing original operations in transformers with their equivariant counterparts. So we embed our input 3D graph with atom and edge degree embedding and process them with transformer blocks consisting of equivariant graph attention and feed-forward networks. So here is equivariant operations, which serve as building blocks for equivariant graph attention. For example, transformers adopt layer normalization to stabilize training. This Ln calculates the linear transformation of normalized input. So each gray line between input and output IRPS features contain one learnable weights. RMS denotes the root mean square. And C is the gate layers are equivariant activation functions where nonlinearly transformed scalars are used to gate non-scalar IRPS features. On D, you see that the left two IRPS features correspond to two input IRPS features. So we use the notion from transformers and message passing and define message sent from node J to node I. Given features x sub I and x sub j on target node I and source node j, we combine the two features with two linear layers to obtain initial message. Attention waves capture how each node interacts with neighboring nodes. A sub ij are invariant to geometric transformation, and thus we only use type 0 vectors. In contrast to dot product, MLPs are universal approximators and can theoretically capture any attention pattern. The output of attention is a sum of values multiplied by the corresponding A sub ij. So values of Vij, these are features sent from one node to another transformed with input-independent weights. We first split f sub ij, where former consists of type L vectors and the latter consists of scalars. Then they use the multi-headed version of the attention. So we have embedding, we have radial basis and radial function, we have feed-forward network, we have output head. And they did experiments on QM9 data, which is a very good data set for graph regression, like these properties that you see for QM9. Also MD517, the energy and force are in units of milli-electron volts. And so this is the results on OCIS testing set.